Hello everyone, and welcome to this video on line integrals on manifolds using differential forms. Now in this video we will look at line integrals on manifolds using the language of differential forms, which offers us a powerful and coordinate independent framework for integration on manifolds. Alright, get rid of that. Alright, so just a little bit of a background. So in standard vector calculus, a line integral of a vector field f over a curve gamma is usually written as the integral along gamma of f dot dr. Now this integral represents the work done by the field f on some particle as that particle moves along the curve gamma. You could think of it as that way. Now the expression dr can be seen as a small displacement along gamma, and f dot dr gives the component of f in the direction of r. All right, so in differential geometry, we generalize this idea by introducing one forms, which capture the notion of a field acting on directions in a coordinate-free way. And you'll see what I mean by directions. All right, so differential forms on manifolds. So on a smooth manifold M, a differential one form, omega, is an object that at each point P belongs to M takes in a tangent vector V belongs to the tangent space to the manifold at P acts on it, and returns a real number. Now I've covered how this works in the first couple of videos on this playlist when it looks at the action of forms on vectors and how they produce real numbers or scalars. Now, intuitively, omega can be thought of as a field that measures the component of a direction along certain axes. So the action of omega on a tangent vector v at a point P is often denoted omega of v. Okay, the result of that, again, if you go back to the first couple of videos on introduction to one forms and one form is gradient and introduction to two forms and introduction to three forms, they're all separate videos, and it looks at this idea and explains the mechanics behind it. So anyway, for example, in R2, with coordinates x, y, a one form omega might look like omega is f of xy dx plus g of xy dy, where f and g are smooth functions and dx and dy are differential forms associated with the x and y directions respectively. All right. Now, line integrals of one forms on a manifold, and that's the subject of this video. So given a curve gamma that maps the closed interval AB to M on the manifold M is the manifold, we can compute the line integral of a one form omega over gamma by integrating how omega acts along the direction of gamma. All right. So what it accumulates, like f dot dr, the work done by the force acting on a particle as it moves along the path dr. Yeah, this integral is written as the integral of omega along gamma. Now, okay, so here we have a manifold M, and we have a local coordinate system on it, a local coordinate system or chart or coordinate system. And I was going to say chart is the one thing, and local coordinate system. Now, on a manifold M, or any manifold, you're unlikely to have a single coordinate system that covers the whole of the manifold. So hence, here we have in the oval shape here, we have the local coordinate system xy, a coordinate chart or coordinate system, or coordinate patch was the word I was looking for. So local coordinate system, or a chart, or a coordinate patch. Three different ways. I like local coordinate system. It's a bit more, explains itself a bit more. Okay, so now in Euclidean space, you could have one coordinate system that's going to cover everything, no problems. But on a manifold, that's generally not the case. And so you have coordinate patches. And this pink one is a single coordinate patch. And for us, we've got the entire curve that we're interested in contained within that coordinate patch. So that local coordinate patch or local coordinate system xy, okay, applies here. Outside in the green bit, we'll have different coordinate patches, different coordinate charts. Right, so here we have a real number line here. We have a closed interval AB, and gamma is a map from this closed interval AB to the manifold M to this local coordinate system on the manifold M. All right, so here's our curve gamma here, along here. Here's just a point picked P, which I'll refer to later. All right. Now, this object over here is the cotangent space, and I'll be dealing with that in more detail shortly. I've elected to put only the cotangent space on these diagrams. That's T upper asterisk to the manifold M, cotangent space to the manifold M at the point P. Here's a point P. Point P is entirely arbitrary. It could be anywhere. All right, we're interested in the point P's that lie along our curve gamma here for this video anyway. I'm going to, in this video, just exclude putting the tangent space, which would be T with no asterisk to the manifold M at the point P, TPM, because I don't want the diagram looking too messy, and it's not really necessary for this video, but a couple of times I will refer to it. Now, the cotangent space and the tangent space are both coincident at the point P, both at the same location, but in the cotangent space live our forms, differential forms, and in the tangent space live our vectors. Okay, so again, gamma is the curve that maps this closed interval AB from the reals to our manifold M. Okay, here's a point P on that curve, which will become more relevant as we go into the next videos. Now, down here, going from the cotangent space back to the reals, is the pullback of the form, differential form omega, along the curve gamma. All right, that's what we're doing. Okay, coming back here. So to evaluate this integral, we proceed by pulling back omega to the interval, the closed interval AB, using the curve gamma. So we'll see how that's done. All right, so the pullback of one forms in the integral. So the pullback of omega along gamma, denoted gamma asterisk omega. That's the pullback of omega along gamma. Is a one form on the interval, closed interval AB. So this pullback allows us to express omega in terms of the parameter t of gamma. So if omega is f of xy dx, our local coordinates over there on the manifold, the bit in pink here, that region in pink, plus g of xy dy in local coordinates, and the curve gamma of t, it's a function of the single variable t, remember t from the reals here, has coordinates gamma of t is equal to x of t, gamma of t. So our vector is given by x coordinates and y coordinates, then by both functions of t. Then the pullback gamma asterisk of omega is where the f is, where the x and the y's are. We're going to substitute in, see that x here, we'll put in x of t, y here, we'll put in y of t. So we'll go this y of t in here, that x of t in there, and then this dx will, by the chain, will become dx dt dt. And the same with the g of xy, same happens there, g of x of t, y of t, and again the dy by the chain rule becomes dy dt dt. Okay, so remember here's our closed interval AB on the reals, it's mapped, gamma is a map from that closed interval to the manifold here to give us our curve gamma in blue. On the local coordinate system within the manifold M, all right, here now at this point P, we have a unique cotangent space as well as a tangent space. The tangent space is not going to be shown in this video, just to save space and not to overcomplicate the diagram. And our forms, differential forms, live in the cotangent space. So T asterisk PM. So this is the cotangent space, T asterisk, to the manifold M at the point P. And we're going to pull that differential form back along the curve. I'm going to pull it along the curve, I should say. So pull back in that sense. It's going along the curve, okay? And that pulls it back to here, makes our life easier. This whole thing becomes a function of t, easier to integrate, as you'll see shortly. All right, so this pullback is now one form on AB, which we can integrate over t. So the integral of omega over gamma, so the integral of omega, our differential form over gamma here, is equal to the pullback of omega along gamma integrated between A and B. So we're going to pull it back to here and integrate it from A to B. When we do that, that's the integral A to B of all of this, and taking out the common factor of dt here. All right, okay. And that is what the integral of omega along gamma is, using the pullback. All right, so the interpretation of the integral of a one form. So the integral of omega along gamma measures how the one form omega accumulates along the path gamma in a coordinate-free way. If omega represents some kind of field, like work or flux, then the integral of omega along gamma captures the total effect of this field along gamma, generalized to curved spaces. Okay, I've been showing curved spaces here. But also, I mean, in Euclidean spaces, it's also just as non-curved spaces too. It's the same process. So let's have a little example now. Integrating a one form on R2 in Euclidean space, two-dimensional Euclidean space. Let's take an example on R2. Let's suppose M is equal to R2. It's going to make life easier. We don't have to worry so much about local coordinate systems now because one coordinate system covers the entire manifold, R2, with coordinates x, y, and let omega be x dx plus y dy. And when I go over the next slide, please try and remember this. Omega is x times dx plus y times dy. And we're going to let gamma of t be x of t. Gamma of t is equal to x of t is t. And y of t, the second coordinate, is t squared. And t is going to belong to the closed interval 0 to 1. Now we want to compute the integral of omega along this gamma. Remember, gamma is x is t, y is t squared, okay, and omega is x dx plus y dy. All right, and t is going to range is going to be over the closed interval 0 to 1, so the endpoints include. All right, so first thing, compute dx dt. If you remember, x was just equal to t, so dx dt will be 1. If you remember, y was equal to t squared, so dy dt will be 2t. Now, the next thing is calculate the pullback omega, or the form that the pullback of omega along gamma will take, so gamma asterisk omega. Substitute x equals t and y equals t squared into omega. Remember, omega was x dx plus y dy. Then we compute, so omega asterisk, gamma asterisk, sorry, omega is t times 1 dt plus t squared times 2t dt. So remember, this was x dx. Remember, dx is 1 dt. This was y, t squared. Dy is 2t dt there. So put all that together, well, take out the common factor dt. And what you've got here is t plus 2t cubed. Next step, evaluate the integral. Now integrate gamma asterisk omega over t from 0 to 1. So the integral of omega along the curve gamma is the integral along the closed interval a to b of 0 to 1 of t plus 2t cubed dt. And of course, break those down into two integrals there, just to make my point. And we'll get here, when we do the integral of this, we get t squared on 2, evaluated between 0 and 1 as a half, and the integral of 2t cubed dt, evaluated between 0 and 1, is t to the 4 over 2, evaluated between 0 and 1, which now gives us 1 over 2. So the integral of omega along gamma is a half plus a half is 1. That's the steps. That's the process for doing it. All right. So in summary then, so geometric interpretation of a manifold. In a general manifold M, the procedure is similar. Define the path, gamma. That's the map from the closed interval on the reals there to M on the manifold. Define a one form omega on M. Okay, in this case, we're just talking about one forms. Use the pullback gamma asterisk omega to express omega in terms of the parameter, the single parameter t of gamma, and then integrate that gamma asterisk of omega over t. All right, now this method is particularly useful in general relativity and differential geometry, where paths and fields are studied in curved spaces. And the line integral of a one form provides a coordinate-free way to measure how a quantity such as gravitational potential or electromagnetic potential accumulates along a curve in a manifold. Because no matter what local coordinates you use, it's going to come back to that single variable you're going to integrate over. All right, so just remembering, here is our manifold. Here was a local coordinate system on it. Now, if our manifold is just R2, then this local coordinate system applies for the whole of the manifold. But in general, in curved spaces, coordinate systems will not cover the whole manifold. And so you talk about a local coordinate system. So we have, in this case, local coordinate system. We're expressing our one form in terms of the local coordinates x, y. Okay, you have an entirely arbitrary point P here. All right. At that point P, there's a unique cotangent space. T asterisk to the manifold M at the point P, the cotangent space to M at the point P, and we have a one form on it, in our case here, and then we're going to pull that back along, we're going to pull it along our curve gamma, okay, so it pulls it back to the one form here that we can easily treat and integrate, okay, along this closed interval here. So the integral of omega along gamma contained in M, gamma here contained in M, is equal to the integral of the pullback of omega along gamma, gamma asterisk, integrated along the closed interval AB contained in the reals. All right. Now remember, don't forget also at this point P there is a tangent space, but I'm in this video not putting it on because the diagram's going to get busy if I have to extend it out here or above or something like that. It's just, and it's not necessary. It's not relevant for the sake of this video. All right. So that's our gamma, our curve is a map from the closed interval AB to our manifold M. Okay, and that happens to lie within this local coordinate system in which we've defined our one form. All right, the one form omega f of xy dx plus g of xy dy exists in the cotangent space to M, t asterisk M. At each point of M, provided f and g are smooth functions on M, I picked one such point, point P, but that point P is entirely arbitrary. The cotangent space for a smooth manifold M, the cotangent space, T asterisk to M, the cotangent space to M at a point P, at a point P belongs to M, is the dual space to the tangent space. The tangent space to M at the point P is shown this way, no asterisk, right? But I've not included that in the diagram, just so I don't make my whole page messy. Okay, so you have the cotangent space and the tangent space. While the tangent space to the manifold M at the point P consists of tangent vectors at P, the cotangent space T asterisk MP consists of linear functionals that map tangent vectors in TPM to the real numbers. So omega is a map from TPM to the reals. And that's contained in the first videos: introduction to one form, gradient as one form, introduction to two forms, introduction to three forms. All in those first 4 videos, I go into that and look at that and just show you that repeatedly, the action of one forms on vectors. All right, and the action of two forms on two vectors, and on two vectors, 2 of them. Three form will act on 3 vectors, and so on. So a 3 form will take 3 vectors in the tangent space and return the scalar. All right, coordinate representation of one forms. All right, coordinate representation of one forms. Locally, if M has a coordinate chart xy, here, the cotangent space T asterisk M at P is spanned by the differentials dx and dy, which form a basis for T asterisk M at P. All right, they form a basis there. Right, remember you had the dual basis, you have the basis in the vector tangent space, and you have the dual basis in the cotangent space. Remember how dual vectors and vectors interact with each other? They're governed by the Kronecker delta, remember, at each point. The differentials dx and dy are dual to the tangent vector basis. Now, tangent vector basis is these partial x, partial over partial x, and partial over partial y in the tangent space to M at the point P. All right, and then they satisfy this condition that the basis one form dx acting on the basis vector partial over partial x is 1, whereas the basis one form dx acting on other basis vector, tangent basis vectors, partial y is 0. So you can see dy acting on that is 0, but dy acting on this one is 1. So you see the Kronecker delta is applying here. All right. Once again, our manifold M, we're talking about here, our local coordinate chart, xy. Here is our curve gamma. It's a map from the closed interval AB here on the reals to here. P is just an arbitrary point on the curve here. And at that point P, you have a tangent space, and you have shown here the cotangent space. I just haven't shown the tangent space, otherwise the diagram gets too busy. But if you look on the previous vectors dedicated to that, I have both, but it's not necessary for this one. So for this first video, I only need to show the cotangent spaces. All right. Next bit. All right. Now, a general one-form omega at P can be written as omega as f of dx plus g dy, where f and g are smooth functions. defined on the neighborhood of P, so they're continuous there, and there's no sharp changes in the derivative, so they're smooth, there's no discontinuities. At each point P, f of P and g of P are real numbers, and omega acts linearly on tangent vectors. V belongs to the tangent space of manifold of P. And again, that's all subject to those previous earlier videos at the beginning of this playlist. Global perspective. Globally, omega can be viewed as a section of the cotangent bundle. Now, the cotangent bundle is T asterisk M. It's not a P. The cotangent bundle is the disjoint union of all cotangent spaces. That's better. All cotangent spaces to the manifold M of the point P. So the collection of all of these for all the different point P's over all points P belong to M. Here, this should just be T asterisk M. Sorry about that. There should be no P there. What it's saying is the collection of all of these ones each, because at each point P, there's an individual unique cotangent space, and the collection of all those, the disjoint union of all of them, is just simply referred to as T asterisk M. Sorry about that. There should be no P there. Over all points P belong to them. If F and G are smooth functions on M, omega is a smooth one form on M. Okay, now I'm finished with that, and I just want to talk about the pullback of scalar functions on manifolds. And a scalar function you can just think of as a zero form. So I just want to go over one time. I have covered it elsewhere. I just can't remember offhand where. I have covered it elsewhere in this playlist. I'm just going to run through it again. So we're going to have a look at a situation here. So finally, the pullback of a function g from n to m. I'm going to give you a diagram in a minute to explain all that. By a map f from m to n is simply a composition of g with f, g composed of f. So let's get all that into a diagram. So here's our manifold M. Here is a map that takes a map from M to N. So it takes points on M, such as P, and maps them to points on N, such as F of P. So one such point, their point P has been picked. Under F, it's mapped to F of P over here. Okay, so that's the map from M to N. You have two separate manifolds, M and N. Okay, now on N, we have a scalar function G, which is a map from N to the reals. So that takes points on N and maps them to the real numbers. All right, G is a map from N to R. Now we can pull G back to M, and what does it give us? Well, pulling G back to M means going back this way around. All right, and what we end up with comes back here, and we end up with G composed of F. So the pullback of G under the map F, so F asterisk of G is G composed of F, which is G of F, and that pulls G back to M here, and then G composed of F is a map from M to the reals. So it takes G, pulls it back under F to here, and then maps that to the reals. So the pullback of the scalar function G under the map F is G composed of F equals G of F. And it simply takes the scalar function G, pulls it back to M, and maps it to the reals. That's it. All right, that's it for today. I hope, or at least for this video, I hope you find that useful and informative. I hope it helps you in your studies or wherever you're at. And thank you for watching. If you will, if you like the video, please press the like button and also subscribe to the channel. And I'll see you in the next video. So please everyone take care, enjoy yourself, and I'll see you next time. Okay, and as we're approaching Christmas, Merry Christmas, and see you all soon. Okay, bye.